In this video, I'm going to show you how we use the dot product to come up with the equation of a plane. Previously, I told you that it's this form right here, 6x plus 2y plus 3z equals 12, something times x, something times y, something times z equals something. Here, I'm going to show you why that is true. So if that why is important to you, then this is an especially important video. So, I'm going to start with something that you all should be very familiar with. Y minus y1 equals m times x minus x1. That's point slope. You know that from BC calculus. One thing I can do with this is change the form. I can move that m times this part right here over to the other side and write it as parentheses y minus y1 equals, minus m times x minus x1 is equal to 0. And remember, that is where x1 comma y1 is a point on the line, and then m is equal to slope. I could break that m down a little bit more in order to connect it more to what I'm about to write, but I'm going to hold off on that for now because I don't think it's worth it right now. So, the equation of a plane is, I'm going to write it out and then I'm going to include a graph for you. It is ax plus by plus cz equals d. That would be a more simplified version, like the one that we had above, or the more common way to figure it out would be a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And I'm going to define all these pieces. So where the vector a, b, c is normal to the plane, and x naught comma y naught comma z naught is a point on the plane. You may say, what about x and y and z? Well, that's like the x and the y up in this 2D equation. Those are the things that change. Those are my variables in my equation. This is a number, that is a number, this is a number, where I've got these values for that number. Similarly, this and this and this, and then this and this and this are all numbers as defined here. Now, I'm going to draw a picture that I hope will help you see this. And I'm going to work this out, right? So I wanted to write it initially and then show you why it's true. So we're going to test my three-dimensional drawing skills. I'm going to draw a plane like so. Imagine that's three-dimensional, right? It's kind of cutting across space. I'm going to put a point on it. Actually, I'm going to move it over just a little bit to here. I'm going to send a vector out like that. I'm going to call that vector, A, comma, B, comma, C. And now what I'm going to do is mark this vector perpendicular to the plane. That's what that little right angle symbol is supposed to represent. Imagine I could swing it around on that plane, and all those, it would kind of trace out that little circle that I drew, and it would be perpendicular to the surface on that plane. I'm going to leave it like that. So now what I'm going to do is label this point right here. This point is going to be P x naught, comma, y naught, comma, z naught. So ABC is normal, and x naught, comma, y naught, comma, z naught is that point, and that should be a parenthesis, not a bracket. Now what I'm going to do, choose an arbitrary point on the plane. I'm just going to call it some point x, comma, y, comma, z on the plane. This would be like if I were to go up top, I got to zoom out a little bit, all the way up to when we were talking about lines here, right here. You know, I could plug in any random x value and get a y, some x, y, z on the plane, and it would be correlated, or they would be defined based on this equation right here. So I could take like that point, or that point, or that point, or that point, right? So taking some x, y, z on this plane, now what I'm going to do is draw a vector like this. So let me go ahead and color code some of these. I'm going to color code this guy like that. And then we will do a green for the normal vector. So that green vector is normal, and the purplish vector there starts at my point x naught, y naught, z naught, and goes out to any point in the plane. So for example, I could take x, y, z, I could take, and don't draw this because I'm going to erase it in a moment. I could take x, y, z out like that. I could take it to that. I could take it to that. All of these would lie in that three-dimensional plane, right? What I want you to see about all of those vectors that I just drew is that I could draw my little circle like this with that right angle piece, and there's a lot going on there, but the green vector would be perpendicular to all of these vectors that are out in the plane. They all start at P and they all end at some x, y, z, all of which are in the plane. And the key here is that this vector is always going to be perpendicular to this vector. So in 3D space, those would always be perpendicular. So I'm going to actually give this green vector a name. I'm going to call it N for normal, because it's normal to the plane. Now I also need to figure out what the coordinate or what the component form is for this vector within the plane. Well, it's actually quite not that bad. So look, if this guy, oh, I lost that. So if it starts here and ends here, all I do is take the ending point and subtract the starting point. So this vector, for example, say this point was 1 and this point here was 3, then the x component of the vector of this purplish vector would be 3 minus 1, which is 2. So I'm going to call this vector here, I'm going to call it v for now. V is equal to, I'm going to take x minus x naught. And then the y component is going to be the ending point y minus y naught, the starting point, comma, z minus z naught. And sorry to get into that other sentence there. And that should be a vector sign, not a parenthesis. Okay, so I got to zoom out. I have two vectors, n, I'll just stick with blue, n equals normal to the plane, and that n vector is a comma b comma c, and I'll show you how we'll figure that out later. And then the vector v is in the plane, and v is equal to x minus x naught, comma y minus y naught, comma z minus z naught. And now here is where we're going to use something from dot product. If A is perpendicular to B, then, and this is a two-way statement actually, then A dotted with B is equal to 0. That's true 100% of the time. If the dot product of two vectors are 0, then they are perpendicular. And why is that? It's because of the cosine theta formula that we had from dot product. So that becomes, look, this guy is perpendicular to this guy. So what that tells me is that n dotted with v is going to give me 0. Why is that? Go back to all of these guys. I'll redraw them. This, all of these vectors within the plane, imagine them spiraling out like the spokes on a bicycle wheel. All of those vectors are going to be perpendicular to this vector. It's like the spokes on a bicycle and then the axle that the bike spins around. This green vector is the axle and these are the spokes. They're always perpendicular no matter which spoke I take. So if they're perpendicular, they're dot product because the v is going to define all of these. Why is that? Is because it's got these x naught, y naught, z naught, and then these arbitrary x, y, z's that are in the plane, right? So that dot product is equal to 0. And then from there, it's just writing the component forms out. N is a, bracket A, comma B, comma C, and then dotted with vector v. I'm just going to copy this. X minus x naught, comma y minus y naught, comma z minus z naught, close. That dot product is equal to 0. And now I just do my dot product operation. And this right here, this is the equation. And you could actually argue that this one is the equation too. And by the equation, I mean this one right here, right? Watch what happens when I do this dot product. I get A times x minus x naught. That's this times that. Next, I'm going to do this times that. So I'll get plus B times y minus y naught. And then the last one, C times this. Not C. C times z minus z naught, close. That's the dot product of that equation that I have up top is equal to 0. And that right there is the equation of a plane. It matches what I set up here, and we can convert it to this form pretty easily. It looks a lot like point slope from 2 dimensions. So if you have questions, please write them down, and we will discuss them as a class next time I see you. I should also add that I'm going to do one more video that actually does this with some numbers. So that will be next in your list of things to do.